My name is Tim Berglund. I work for a company called StarTree. We make a managed cloud service based on Apache Pinot. This talk is about Apache Pinot, substantially about how Pinot works on the inside, because that's kind of fun to talk about. I think in terms of what really matters, unless you're going to operate your own Pinot cluster someday, is why there's a Pinot. And I think there are really two big reasons. I'm going to give you one of them up front, and I'm going to give you another one of them at the end. The two real things that are going on under the covers of why this new database exists. Before, I just feel like I'm looking out here. We need a selfie. We're just going to stop here. So could you just wave? Could you just say hi? There you go. I'll post that later. You look great out there. That's really what this is about. Also, before we get started, I want you to, if you'd like, take a picture of this QR code. And what we're going to do here is I'm going to give you t-shirts or other things if you want. So what you do is you visit that QR code later on, and you join that Slack, and you find me, Tim Berglund, and you message me. And if you live tweet, like a threaded tweet, this talk, or afterward, if you want to write it up, post it on LinkedIn, a little summary of the talk, send me a link to that in Slack, and I will send you coins in our swag store, and you can get a shirt or something, or a hat, or whatever it is. I'm going to send you enough coins for a shirt, but you get to spend them the way you want. You're an adult. I'm not going to tell you what swag to get. So let's do that. It doesn't even have to be complimentary. Oh, sorry, still phone out. You can flame me, and according to the rules here, I'm still giving you a shirt. So just trusting that we all have a good time here. But let's start with a history. I told you there are two motivating factors for why Pinot exists. And I really just tend to look at these things historically. So let's just go back to the beginning of commercial computing. This is an IBM 1401. I just moved to Mountain View 3 months ago. I'm a few miles down the street from the Computer History Museum, and there is a live, restored, functioning IBM 1401. They run punch card batch jobs on it every Saturday, most Saturdays. And that's what computers were. They were batch analytics machines. You put data into them, and they grouped and aggregated, and they put a smaller set of numbers out that you could make sense of. That's why commercial computing started. The idea of a transactional database, that's an anachronistic concept. Didn't even come along until a few years later, because computers had to get powerful enough, fast enough, that you could even hook up a terminal to them, and that was a meaningful thing to do, that you could run software that you could interact with. This is about 10 years later. You might just venture a wild guess that this is somewhere in the middle of the 60s or early 60s, when now mainframes are fast enough that we can have the idea of transactional data. Transactions were an addition to analytics, where things started. Well, reporting at this point, do you have any idea how hard it is, by the way, to find a picture of green bar? If you could, I'm open. Send me a Slack message to a better picture of green bar. I need to find green bar, produce my own stock photography. This is a major crisis. Anyway, reporting was a feature of that software. You had a terminal, you did stuff, and that stuff is, CRUD over entities, basically. That's what you're doing. There's stuff in the world is changing state. You're typing things that reflect those state changes. They're remembered in a database. And then reporting is a feature of that software. And so analytics, transactional data, all this, it's all just of a piece. It's all one big blob of stuff, and it's fine, and the world is great, and it really works until it doesn't when this thing comes along. Computers get fast enough that you can put one on the desk, and it's got a display, it's got storage, it's all this. You do things, you play games on it if you want, you do spreadsheets. I was a teenager, reading about this in magazines. People were talking about this client-server revolution that's going to change in breathless tones, like are there cars burning? Are there people dying in the streets? It seems like a big thing that they were talking about, but it really was a major revolution in the way hardware was procured, in the way applications were built. So if you're a mainframe developer and now this happens to you, completely different way of building applications. The folks who lived through that, and I'm not one of them because I was a kid reading Byte magazine, I wasn't a professional software developer, now had software running on these clients and data that lived in a closet on one of these, running on a database server. And so that data that was nicely tied up in the mainframe, and it was all there. All the transactions were there. The reporting software ran. It was a wonderful time to be alive. Then it was spread out. Everybody's got their own, every minor executive procures budget for their own application, their own data. All the data is all over the enterprise. Okay, so that revolution in application architecture broke the way we were doing analytics, and we had to come up with a new thing, which was, of course, we put, this is an anachronistic phrase, but I hope you understand the movie reference, top men on the project of the data warehouse. Okay, so the data warehouse was a response to this revolution in application architecture, and it was a great idea. Old-fashioned term now, right? But we had to build that because everything else changed. The way we built software changed. The web happened a very small number of years later. This is almost contemporaneous. And when the web happened, client-server had become an established paradigm, but it was still kind of new. And the folks who were building the web, the first interactive websites that weren't just static content, took that paradigm and used it. That's what you did, right? This is the thing that we've got, let's use it. And it kind of worked fine. The client-server completely survived the internet revolution, apparently unscathed. The data warehouse started to get a little, kind of squished by scale, and there's a little pressure on things. And the data warehouse, after a little while, gave way to, this, by the way, is what a stable diffusion algorithm came up with to describe big data. I love it so much. I can't not use this image like for the rest of my life. And that was really just that same data warehouse paradigm, but make it bigger. Still batch, still take all your transactions from over there, put them here, just kind of do it a little different, right? It was data warehousing writ large. And at the same time, people are starting to talk about how nobody says client server anymore, we say monolith, and this monolith is now a bad thing. That application architecture wasn't scaling, and neither was the data warehouse. To make it worse, at the same time, mobile devices became a thing. Kind of weird to think about, but big data, when that happened, and the penetration of the iPhone and things, all kind of happening at the same time, right? So now you don't go to a computer and use the internet, you have a pocket computer, you're constantly connected. Your commercial and social life is mediated electronically through a device in your pocket that wiggles when things happen in the world. And that the cultural and personal and relational import of that is a different talk for a different conference. What happens in response to these things? The slow death of the monolith, maybe the somewhat disappointing performance of the data lake. Well, here we are. We're at current. We're mostly talking about Kafka. And event-driven architecture really begins to rise as a response to this. People no longer build one giant system with one database at the center and a giant sclerotic application on top of it, but lots of services that talk to each other over events. This impacts the way we build applications. It is the second major, in my interpretation of the history of computing, disruption in application architecture. Client server was the first. Here we are 40 years later, there's another one. And now, instead of a database, all of our data goes here. And it's great until it's not. What happened with the first major disruption in application architecture, client server? We had to come up with a new way of doing analytics. Well, here we are again. And that's where Pinot comes in. So let me spend about the next 20 minutes talking about how Pinot works in whatever level of detail I think is relevant and interesting here. And then I want to spend a few minutes looking again at that history, and I want to unpack another important thing that's going on in the way we interact with our electronic life that Kafka is a part of and that Pinot is a part of. So let's just dive into some architecture. Here you go. Good. Glad that's covered. Moving on. No, so let's dig into this a little bit. Let's uncover what the pieces of this are. That's a nice diagram. We kind of have to build it piece by piece for it to make sense. But let's step back and think about what data looks like in Pinot. Pinot's a database. It just does. I remember 10, 12 years ago, new databases, it was like, okay, so we don't use tables. There's this other thing we do. Nobody really wants that anymore. Everybody just wants tables. Pinot uses tables. There's columns. They have names. They have data types even. So this is not interesting, and you don't want this to be interesting in a database. And I'll save you some time. You query them with SQL. I will not have any slides with SQL on them because I don't want to insult you. All right, yeah. You store data in tables. I think the most interesting thing about the way this happens in Pinot is there is no create table statement. Pinot DDL, we kind of said, that was going to get ugly. Can we just use JSON? And so there's a JSON file for specifying the configuration of the table. And actually, a lot of your sort of life as a developer using table honestly revolves around that file. And we won't go into it in this talk, but there's a lot there. Schema is a separate file that you break out, so you can have like multiple tables that use the same schema. That's kind of cool. There are different kinds of tables. There's tables that derive from piles of batch data. There's tables that you ingest from Kafka. There's tables that are both. Those are all interesting kind of things down in the weeds. But it's tables, right? Tables are broken up into little pieces called segments because Pinot is designed for large amounts of data that are going to scale over lots of machines. And a segment is just a slice of a number of rows, some number of rows of tables. So roughly speaking, a time partition of rows. I said that to a group of folks who were heavily invested in a particular bitemporal database that is associated with a particular species of Lisp. Let the reader understand. And they're like, okay, so when you say time partition, I said, no, we're not gonna do that today. But you get the idea. You go from like this row to this row. That's a segment, and a table is made up of those segments. It's pretty simple. It's interesting to look at how segments are put together. So imagine if you had clickstream data. There's lots of different kinds of data that people put into Pinot. It's really not, it didn't come from the world of web analytics, but it's fine. You could put clicks in there. If you had like a record that looked like this and you were ingesting that into a table, because Pinot is an analytics database, it's not ever really interested in getting a row out, right? You don't do that in analytics. You don't say, hey, what's the order ID so-and-so? That's what you do in a transactional database. In an analytics database, you are more likely to want to say, well, this section of rows, this collection of rows, let's scan a particular metric value, some column from those rows. Let's get all those and compute an aggregate over those. That's a typical filter and aggregate kind of analytics operation, sort of bread and butter analytics operation. So what you do inside a segment, you don't put each individual row together, but you gather up the columns and you serialize all those columns for the number of rows represented in the segment all together. And so you kind of have to build this in a chunk. If you're ingesting batch click data, you're going to say, all right, we'll take these 200,000 rows, build a segment, and then write that segment off and load it into the cluster. But inside each one of those columns, those chunks of columns, you've got actual all the values of that. Each individual row's value for that column all serialized together. So if you wanted to compute an average of this metric, bytes, you could just scan across those if your indexes were arranged such that you were able to do that, and you'd have a nice, efficient sequential read over those things. That's just a typical way that a analytics database is built. So we've got segments, lots of different segments being built all the time. Segments being thrown out because they're too old. You can specify a maximum age. Segments are stored on, this is actually what they're called, servers. Naming things is hard. Servers are the machines in a Pinot cluster that are sort of the real heroes, right? They store the data. They do most of the query computation when it comes to actually doing the compute over a query. There's some important decisions there reflected in the design of Pinot to keep storage and compute tightly coupled. I don't give a lot of benchmarks in this talk, but you can have terabyte to petabyte sizes, the data sizes, and for certain kinds of queries, still get results in the under 100 milliseconds kind of time frame on actual non-pre-computed filter and aggregate type queries. You can have queries that run longer than that too, of course. You can have whatever you want. But to get on the order of 10 to the 1 millisecond query latencies, there are certain engineering decisions that have to be made, and tightly coupled compute and storage is one of them. So it's not, servers have a lame name, but very important design decisions represented here that are essential to Pinot's performance. So data gets stored on servers. There's another machine called a broker, and that's where external clients interact with. You'll throw a little piece of JSON at a API endpoint on the broker. The broker will look at that query, look at the table referenced or tables and the indexes that exist, and it will decide how am I going to route that query to servers. And very complex topic worth, boy, we could do a half a day on that. It's kind of funny. I'm just recently digging into the details of query routing. There's a lot there. The broker does some routing, and it sends queries. It scatters the query to the servers. Servers do that computation, and results come back to the broker. Broker kind of combines those results and sends a result back to the client. There's a brand new feature in Pinot 1.0, which just dropped last week, that does a more complex thing where it'll say, hey, I need these 4 servers to do these 2 subparts of the query, then stream your results back to this tier of servers that'll do some other level of the query, and then to this, it's this big multi-stage engine for things like nested queries and joins and window functions and things like that. But the simple version is this. There you go. There's also the thing called the controller that does cluster management, makes sure the brokers are up to date with state changes in what segments are stored on what servers and what servers even exist, and all that metadata is persisted in Zookeeper, and now you kind of have that picture back. Minions are this kind of built-in distributed computation framework. Sometimes you got to go do things, like you got to go scrub through a table to find things that need to be eliminated for GDPR reasons or something like that, and maybe go rewrite some segment files, because segment files are immutable because it's an analytics database. We provide this mechanism called minions, where you can just go run those tasks and they'll go run in the background and not burden servers with that work. So that's kind of the physical architecture. Let's talk about some cool indexes. That's always an important part of the story. These are the main indexes. I want to tell you about one really trivial one, a couple interesting takes on that, and then the coolest index that is the most exciting one in the whole world of Pinot. The forward index. Now, remember that segment picture where you just had those chunks of columns? So a row internally to Pinot gets an ID within a given table. Each row has an ID called the document ID, abbreviated doc ID. It's not the primary key. You can define a primary key in your table config file, but it's an internal representation of what that row is. And this matters for a number of reasons, not least that there is no place on disk that that row actually exists, because it's a column-oriented database. You've got little chunks of the row everywhere. And so the forward index exists on a column to say, if I know a doc ID, maybe better with a picture, I have a doc ID and I know what column I want. The index exists on a column. Get me the value for that doc ID. So it's like I know this abstract definition of the row. Tell me what the thing is. And this is showing a low cardinality column and dictionary encoding, which is a thing that Pinot will try to do aggressively if it can on dimension type columns. So yeah, it's like I know the row. Tell me the value, which helps us understand the inverted index, which really is that flipped around. If I have a value and I want to know what rows that appears in, I can use an inverted index to say, all right, well, prog, what doc ID has prog? Oh, that's 3. Okay, there you go. Then I know what rows that occurs in, which might help me filter or might help me avoid scanning other things down the line that I might want to avoid scanning. Because that's really one of Pinot's goals in the read path, is to scan as little as possible. You'd like to avoid it. It's a bad thing. It's slow, takes time. Avoid it if you can. That works on relatively low cardinality dimension type columns. But what if you have something that's a number? Numbers, like a real number, an integer, or something like that, we tend to think of them as continuous. I mean, they're still discrete, but they've got lots and lots of discrete values. They don't bin up so well. The range index artificially creates bins. So if it's temperature and it's a real number anywhere between 0 and 100 Celsius, I can make 20 bins of 5 degrees each, basically just build an inverted index on that. So it's a way of adding inverted index functionality to a real valued or integer valued numerical column. Likewise, timestamp, same thing, but with attention to the way time works. So this, I believe I have a picture, yes. So I've got some nice ISO 8601 timestamps there. Still not sure why I left seconds off. That seems rude. Seconds, what did they ever do to me? But you get the idea. If you have that full timestamp, you get to specify in defining the timestamp index what grain you want. And if I want day grain, then I'll zero out milliseconds, seconds, minutes, hours, bingo. I basically can just create a range index on that fake timestamp that I've created and get all the documents that occur inside that unit of time based on my grain. So same trick. It's like this inverted index showing its, nosing its way into other data types. There are others. There's a JSON index. There's a thing called a Bloom filter that isn't really an index, but it always tags along with the indexes. But let's talk about the star tree index. Now, not to be confused with star tree, the company. The star tree index, gotta say them just slightly differently. Actually, it was called that before star tree was called star tree. So our name is an implementation detail that leaked into the interface. It happens. This is the only place pre-aggregation of any kind occurs in contemporary Pinot. And it's automatic. Now, folks who were doing user-facing or real-time analytics before databases like Pinot, your choice was to compute aggregates yourself and put them in a key value store, basically, because key value stores are the only thing fast enough to put in the user interaction layer. There's very little pre-aggregation in Pinot, but the star tree index does that. So for the case where the query is a filter and aggregate, let's say the aggregate is sum and the filter is one of 3 dimensions. You don't know what they are, but there's 3 dimensions. They might show up in the where clause in some combination, and whatever they show up, they'll filter, and you'll aggregate, you'll sum up this other metric. Bread and butter query type. Star tree index optimizes that. So clickstream data. Plenty of good people want to measure clicks. It's not just terrible, manipulative, weirdly behavioral ad tech companies. There's some decent plays here, so let's give them their due. I got 3 dimensions, country, browser, and locale, and 1 metric, ad impressions. I want to sum impressions based on those 3 dimensions. This is really cool how this works. It actually builds this tree in the index itself and avoids ever having to scan the data. So each node in this tree, it's able to traverse this tree no matter what combination of the dimensions show up in the where clause and get the pre-computed aggregate straight out of the index. So if I wanted, I always forget, I think I'm going for all of the Spanish speakers. Let's traverse the tree. So we'll go over here. First, we'll say, okay, country doesn't show up in my list of predicates, so I'll go to the star node, the wildcard node. Browser doesn't show up in my list of predicates. I'll go to the star node there. If I wanted like Safari, I'd go to the Safari node, but I'm going to go to the wildcard node, and I'll say, okay, all of my Spanish speakers in my entire ad network, there they are, 500 impressions, done. It's right there. People, when they first get benchmarks with this index, one of the keynoters referred to people thinking something was broken and an alarm going off because it seemed too fast. This also looks suspicious to people when they first see the results. It looks, it's got to be cached or something. Restart this, it's wrong. So yeah, another example, if you wanted in Canada, all of the English speakers. So you saw that browser is wildcard, you go to English speakers there. So you have log n access to those aggregates. Super cool. It's a really cool index type that is pretty impressive. All right, how are we doing on time? We can talk about how data gets in. We'll have some fairly simple data set. This actually comes from a recipe on the StarTree developer website, dev.startree.ai, for ingesting static batch CSV data into Pinot. We want to get that into a table. And again, that's going to create, well, one segment in this case. It's not a whole lot of data, but that would normally create segments from this batch ingestion. This, by the way, I mentioned minions as that distributed computation thing. This uses minions under the covers. You don't know that necessarily going through the commands, but it kicks off a minion task. All right, so we'll take this data, define a schema, and just to kind of put this in front of you, I'm not stepping you through this a piece at a time. I'm not expecting you to remember these things. It's in the docs, but the schema looks like this. It's some really nice, friendly, readable JSON as a separate file. Again, so if you want multiple tables that use the same schema, you could do that. And here I should point out, you break the columns into three types: dimensions, metrics, and date time is a special type of dimension. Then you create a table config file. This is a very, very simple table config file. Table config files get, I'll just say, somewhat less simple than this. But again, some nice JSON, easy enough. You add the table. The only time I will ask you to write any YAML is here. The ingestion spec to do that ingestion, it looks like a lot for 4 lines of CSV, but normally it's some large collection of things off in S3 somewhere with subdirectories, and get this part of the file name and turn it into a column, and there's a lot of crazy things you need to do in there. You do that YAML, kick this off, that goes starts a minion, creates the segments, pushes them into the cluster, and you've got data ingested. You can also kick that off. There is a SQL way of initiating that that would probably look better on the slide, but I have made the choices that I've made. All right, when you do that, like I said, the controller sends a task to the minion goes and reads that CSV, actually creates a segment file, sends it to the controller says, all right, server, I'm going to put it here. And by send to the controller, that doesn't necessarily mean literally stream bytes to the controller. There's lots of ways that goes down. The details are not important. And as that ingestion goes on, new segment files are pushed, and you get segments. Now, I want to talk about how that works in the streaming case. I want to try to leave a few minutes for questions. So let's just talk about streaming ingest and see where we get. Now, when we are consuming into a table from Kafka, it's a different kind of table. In the table config, you say this is called a real-time table. And in that table config file, I'll show you in a minute, you actually have the bootstrap address list and credentials and the name of the topic. The table itself is connected to a Kafka topic. And the records in the topic, Avro, JSON, whatever they are, those field names correspond to the field names in the table. So it's this direct ingestion. And we still have to play the same game. We still have to create segments and push them to servers, but we don't want to batch up messages for 10 minutes before you can see them. So what happens is they're consumed into an in-memory data structure that looks to the system just like a segment, but it is in fact in memory. So Pinot is acting as a Kafka consumer. There is no Kafka Connect anywhere. And as it ingests or consumes a message from the topic, it puts it in the segment, and it's instantly available for querying. So freshness is one of the things that we need in a real-time database. You don't want to wait 5 minutes. That could be the difference between usefulness and not. So as soon as that message comes in from Kafka, it's queryable. It's in the consuming segment. But being an in-memory thing, it fills up, and eventually we flush it to a segment on disk and save that there. So same thing. I've mentioned that the Kafka config goes in the table config. So that real-time table is just one-to-one connected to a Kafka topic. No, it's fine. I didn't think that was an applause line, but I think they were a little more into it. I want to emphasize a point here, skip ahead a little bit. If you imagine a partitioned Kafka topic, Pinot was created at LinkedIn just a few years after Kafka. So it very much grew up because of this kind of hole in the stack that needed to be filled. And it, to some degree, co-evolved with Kafka, and its integration is therefore a very intimate one. Again, it's not just Connect and JDBC or something like that. It's a consumer, and it's even partition aware. So, we've got, say, a topic with 3 partitions. We can have it map where those segments go, and we can actually have 3 separate servers in the cluster be 3 separate consumers, each one of them consuming one of the partitions, and consuming segments filling up and flushing segments to those servers. And the cool thing about this is sometimes the partition key in the Kafka topic is a thing that's going to show up in your analytic queries too. Now this is only a sometimes, right? This is not all of our queries and indexes are all optimized this way. But when they are, you can do this thing where you say, well, to pick that partition key, tell Pinot what hash function is being used on the Kafka side, and messages then get assigned to Pinot segments based on what partition they come in. So we might then have data locality when our queries line up this way. You have the option of getting data locality kind of for free because of that very intimate Kafka integration. So it's a nice thing. Wrapping up, shall we remember our history? And I said there's the history and there's another element here. We had mainframes until we had this thing. And when we had this thing disrupting what had been a stable application architecture paradigm, we needed a new analytics paradigm. Multiple billions of dollars of enterprise software sales, consultancies, publishing empires, careers launched based on the data warehouse, and it's not a bad thing. The web and mobile didn't instantly unseat those technologies. They just put pressure on them until we saw that they didn't really work anymore. And so now we have what we've got. So 2 things happened there. One was we, as developers, have been thrust into this new and somewhat uncharted world of event-driven architecture. I think Jay mentioned this morning, there were papers in the 90s. Every time I'll say it's a new idea, somebody say, well, actually, it's, yes, I know. But for it to be a mainstream thing, it actually is a new paradigm in the last 5 or so years. And we are kind of all building our first system. We don't really know what the stack looks like. It's great to have things in logs. It's hard to ask questions about what's in logs. And you can see that. You can go walk around the expo floor and see there's different sponsors and different businesses, different approaches to answering that question of how do I know what happened? There's like a transactional lens on that. There's an analytics lens on that of how do I know what's happened? So that creates, a new opportunity. But there's another thing. What people were saying when the data warehouse was new was all the data in the business is locked up in these departmental database servers and random files on file servers, which was a thing people said back then. And you can't see it. It's scattered all over. Decision makers can't get a single pane of glass. And the data warehouse did that. That whole ETL idea was to go get all that data, put it in one place in a format that we could report on efficiently, and write reports, print them out on a laser printer, and give them to a decision maker so that decision maker could see what was going on in the business. That was all batch. Okay, it was all next day, which was groundbreaking and amazing that you could do that the next morning. But the idea was to enable decision makers to see what was going on. The data's locked up, you can't see it, let's unlock it, get in front of the decision maker. Let me show you one use case that I hope is viscerally interesting to everyone. Meal delivery. Now, meal delivery pretty much on the planet, it's only a slight exaggeration, if at all, at this point, that you can't get a meal delivery on planet Earth without Pinot being involved. We're very successful in this particular vertical. It's not the only one, but here we are. I like burgers. I'm an American. I make no apologies. That little number right there, that's analytics data exposed to us. This is DoorDash. I don't work for DoorDash. I have friends who do, but I'm not an executive there. Nobody gives me reports on things. I'm not a decision maker. I don't shape that business. I kind of am a decision maker, though. The idea here, this is the other shoe dropping. All right. The first one was, oh crap, I knew how to build monoliths. I don't know how to do everything with Kafka and microservices now and still have queries. What do I do? Help. And Pinot's like, I'd be happy to. But the other thing happening is this other revolution where the data inside the business can now power features that are actually exposed to users. So the community of decision makers is not just relatively well-dressed people with slightly nicer offices who work for the company, but it's every user of the product or service. And this is a very simple way to understand how that data can be unlocked and exposed as a feature. I obviously want to know how long it's going to take for my burger to get to me. Many, many events must be filtered and aggregated to make that, and it has to be fresh data. And I am updating search results. I'm not going to wait 15 seconds for a Spark job to run, okay? I need tens of milliseconds of latency. There need to be hundreds of thousands of queries hitting the database per second, in this case, and that data needs to be not more than a few seconds old. And all of those seconds had better be the streaming pipelines before it gets to the database. We're not going to add more time once it gets into Kafka. So latency, concurrency, freshness, those three things are simply different, and you have to engineer that database differently to deliver on this. But what's happening is people are discovering that taking the data inside the business and exposing it to users creates a stickier and more valuable experience for us, for a guy who wants a burger, or a person using LinkedIn, or somebody with a flower shop or a wedding invitation site using Stripe, wanting to know what's going on with their merchant dashboard. Little stuff. It's not giant players. It's ordinary people getting access to the database inside the data inside the enterprise, and now being included in the community of decision makers. This is why your users need your data, and Pinot needs to serve it to them. Yeah, that question is, I think, being fundamentally transformed, and the answer is all of us. So, with that, let's cut it off there. I'll be wandering around. I don't want to go over time. We've got another talk coming up here soon. Thank you very much. Go join that Slack workspace.